Well, so objective that we're going to cover in this segment are the first thing that we have is the stationary point key concepts, which is understanding the key concept of maxima minima. We're going to talk about inflection as well. So we're going to talk about what are the different criterions for stationary, and there is something called as non-stationary point of inflection. So well, let's start with the first part, which is finding the coordinates of the maximum point and minimum point. Now, before I do anything here, I'm just going to touch base upon the previous part here. That like when you look at the minimum, it looks like a concave up. This is like concave up, and this maximum, local maximum or global maximum, whatever it is like concave down. This is referred as concave down, and this is referred as concave up. This is referred as concave up. Now, when you're finding out the maxima minima or point of inflection, you have to have like very clear ideas about where is the function increasing, decreasing, where is it is concave up, where it is concave down. So all these parts now we're going to start covering up. So let's begin up with the first part, which is like finding the coordinates of maxima and minima. Well, so let's take an example here. That is, assume that this is the curve. It has got, let's say, a maximum point here. This is called maximum point. This is your minimum point. And these are called as local maximum and local max or local minimum. So local min, because you can clearly see that there are some y values which are going even higher than this y value. And there are some y values which are lower than this y value. So that's why these terms are referred as local max or local min. Now, there are a couple of interesting things that we got to do, understand in order to understand the maxima minima. So first thing is that you understand here that here the slope of the tangent which you draw. When you draw the slope of the tangent at this point, the tangent is actually flat. And even at this point, the tangent is flat. So at least to get the coordinates, now at these points, you're going to equate them to 0. So dy by dx, equate them to 0. So I'm just going to keep summarizing here. Let's say this is my dy by dx. First step is to find this. And to find out the coordinates, you equate to 0 and solve for x. Solve for x. Now, once you solve for x, you have got a dilemma. Okay, now at both maximum and minimum, the derivative is 0. So how do I know which one is maximum actually? So I'm going to do the verification now. After this is the verification step. So the verification can be done using two different ways. Number one is using the sign diagram of single derivative. So I'm just going to project these points onto the single derivative sign diagram. So you can see that critical point I'm just projecting on the line for the single derivative. Now my single derivative here you can see is negative. So here it is negative and here it is positive. Sorry, here it is positive, that slope is positive, and here slope is negative, so that's why it is negative. And once again the slope is positive. So this is the sign diagram for the derivative. Now suppose if this is my point, if I solved for this and I got, okay, x is a and this point is x is a, and if you draw the sign diagram, if sign changes from positive to negative, it means like it's a maxima. And if the sign diagram changes from negative to positive, it's a minimum. So it's a straight observation, and you can give your conclusion that it's a minimum point or maximum point. Now, taking an example that I can give here is, let's say y equals to x cubed minus, let's say I can take minus 6x. Now, or if I take x cubed minus 4x, here I'm going to do dy by dx is equals to 0. So I can do 3x squared minus 4x minus 4. Or I can take another function which gives me better x values. So I'm taking my x values as, let's say, x cubed minus x straight away. I'm going to take x cubed minus 3x. So now if I do the derivative, I'm going to get 3x squared minus 3. So when I do 3x squared minus 3, I'm going to equate this to 0. And I'm going to solve for x. So that gives me x squared is 1 and x is plus minus 1. Now, when you draw the sign diagram about plus minus 1, so this is minus 1, here it is positive 1. Now, when you want to check whether it's maximum or minimum, you're going to draw the sign diagram for this. So let's say if I plug 0 here, if I take 0, it is negative. So it is negative here. If I take positive 2, it is positive. If I took 2 times 2 square is 4, 4 times 3 is 12, and it is positive. And then once again, if I take here maybe minus 2, you'll notice that it is coming positive. So as if you look at now, the first value, the y value, the x value around which the slope is changing from positive to negative, it's referred as max point. And here it is referred as a min point because slope is changing from negative to positive. Once you get this, you're gonna now check uh, the y value. Like, how do I get the y value for these x? So you can just plug in x as minus 1 and let's say plus 1 at these points. So when I plug x is minus 1 and x is plus 1, you're going to get the y values. So this is how you find out the basic coordinates of the maximum and minimum points. Now, after this, what happened is there are some cases your sign diagram doesn't change. So I'm going to just quickly go through with you about the sign diagram not changing. Now, there are certain examples I can take is, let's say y equals to x cubed plus 4. Now, when I do the derivative at this point, dy by dx, I get 3x squared. And if I equate to 0, I get x is 0 itself. Now, when I draw the sign diagram for derivative, so dy by dx, I notice that, okay, here my slope is not changing. If I take minus 1, it is positive 3. And it is, if I take even plus 1 and input in the derivative, it is coming as positive. So I'm getting the derivative 0, but the signs about both the signs about that point is actually the same. So in this case, this is actually referred as something called as, so the function is actually, it's like this, then it's increasing, it's stationary for some time, and this is again like increasing further. So when you're like here, it is increasing and then again increasing. So this is referred as actually as a stationary point of inflection. So this is referred as stationary point of inflection. Now, for stationary point of inflection, generally your dy by dx sign diagrams should be the positive positive or negative negative. So in this case, in the case where the signs doesn't change, there is a possible point of stationary point of inflection. Now, inflection is a point about which concavity changes. So one side it will be concave up, the other side it will be concave down, or something like that. So I'm just going to touch base upon that concept later on. But as far as the single derivative sign diagram, basic key concept of maxima, minima, and all are concerned, this is how is the summary. The question, the map, if I draw, now here we have got dy by dx. You input, you solve for x, equate to 0, solve for x. So you solve for x. Once you solve for x, you get some coordinates. Now you draw the sign diagram for dy by dx about that point. Sign diagram. Once your if sign diagram is positive, it is positive to negative about that point. It's a maxima. If sign diagram is let's say negative to positive, it's like a minima. It's this way. And if sign diagram doesn't change, if it is positive positive or negative negative about the point A, then it is a stationary point of inflection. I'm going to cover up this in the next segment, but at least this is the preliminary analysis about the points being maximum or minimum. So this is how you use the single derivative to find out whether the points are maximum, minimum, or if there is any stationary point of inflection. I'm going to use the second order derivative in the next part in order to explain the same concept of finding maxima, minima, and its verification.